Alright, so let me start this here. 6.4. We're going to look at product to sum and then sum to product. So we're going to go one way, then we're going to go the other way. Alright, and what these formulas are for is to help us solve equations. That's it. That is the end of it all. If we can solve some trigonometric equations, that's what we need to do using these things. Okay, so this formula is found on page 606. Of these formulas. So notice what we have here. This is called product to sum formula. So if you see a cosine of x multiplying another cosine of y, again different different angles, what we can do is we can split them off into just sum formulas. Again, sometimes helps us. Sine of x times sine of y. Again, there's different formulas there. I'll give you guys a few seconds here to write those down, or maybe just flip open your textbook to page 606 just so we're on the same page there. Alright, let's go for it. So first things first, practice problem number 1. Can we write cosine of 3x times cosine of x as a sum or difference of the two other trigonometric functions? And again, it's just going to be making sure you can look at the formula, use that formula to change that to a sum. So let's go for it here. Again, cosine of 3x times cosine of x. Which formula we're going to use? 1, 2, 3. We're going to use the first one from the previous slide. So it's 1/2. Put a little bracket in. It's cosine of parentheses. Now it's the formula says x minus y, but we understand it's x is the first angle right there. Subtract the second angle, which is x here. Close off that parenthesis, and again, all I'm doing is I'm just following the formula from the previous slide. Plus sign, cosine of, now what we're going to do is we're going to add the two together. So 3x plus x, and then close it off with a bracket. And we got to simplify. And of course, you don't have to write it like this. I think you can probably do 3x subtract x to make it 2x easily enough. So it's really 1/2 bracket cosine of 2x plus cosine of 4x. So notice these are not the same angle, so you can't really add them together. They're not considered like terms. You keep them separate, but we do have to distribute the 1/2. So how about 1/2 cosine of 2x plus 1/2 cosine of 4x. There's our final answer. Alright, another additional way this helps us is the whole concept. Remember, we started off even Tuesday talking about we can finally get an answer of degree values that are not multiples of only 30 and 45, but we can actually figure out degrees of maybe 112.5 degrees because of the half angle or the double angle formulas. Well, the same thing works here. If I can use this to solve or simplify trigonometric functions of certain variables. So practice problem number 2. Question is, can I find out the exact value of sine of 15 degrees times cosine of 75? Alright, so let's see. This is a multiplication between a sine and a cosine. If you look back at the previous slide where we had our rules here, that one's going to be the third one down. It's sine times cosine. And we're going to follow that again. So sine of 15 degrees times cosine of 75 degrees equals 1/2, of course, bracket. This time it's sine of x plus y. So how about 15 plus 75? And again, you can probably skip this step, go down to the next step, because I'm sure you guys can add 75 and 15 together. Sine of the subtraction between the two. So now we've got 15 minus 75. But you probably should be able to go directly to here. How about this? 15 plus 75 is 90 degrees. And then 15 subtract 75 is 60 degrees, or negative 60 degrees. Probably can go directly to this one. I think you guys can figure this one out. I think you guys know what is sine of 90. Sine of negative 60 may be a little tricky. All right, anybody, sine of 90 degrees. Good, I almost heard 1, that's good. 1/2, sine 90 degrees is 1, and sine of negative 60 degrees. Hopefully we'll learn how to do this one here. Remember, sine is a odd function, so this is what we do to make it easier. We want to take sine of positive 60, so what we do is we just move this little negative on the outside, because sine is a odd function. So that becomes a minus sine of 60 degrees. All right, where does that come from? If you want to just kind of quickly look at it. Let me see if I can find it real quickly in our textbook here. I think it was 6.4, I think, when we reviewed all the rules here. No. 6.2, 6.1. 6.1, when we're reviewing the rules here on page 569. Page 569, and it's the even-odd identities. Got a few people turning in their textbooks here, so I'll wait a little bit. All right, page 569, and you look at the fundamental trigonometric identities, and it's number 4, even-odd identities, and it's negative sine of negative x is equal to negative sine of positive x. That's how you get rid of negative angles inside sine. But anybody, what is the sine of 60 degrees? One thing we can do is build ourselves a 60 degrees here like this. Go up like this, because 60 degrees will be closer to 90. And here's what I think. I think which one's going to be the longer side? This way or this way? Or the shorter side? The shorter side will always be 1/2. The longer side of a multiple of 30-degree angle is going to be always this. So then I say my x value, my y value. And sine is going to be my y value. Okay, good there. Building a quick triangle. I'm going to erase it here though real quick here, so I have room here. So I got 1/2 bracket 1 minus root 3 over 2. Distributing. Oh no, I can simplify the stuff inside the bracket first. So 1 becomes 2 over 2. Simplifying that out becomes 2 minus root 3 over 2, and then multiplying finally by 1/2 gives me a final answer of 2 minus root 3 over 4. Ha! Honesty question, of course. How many read 6.4, 6.5 prior to coming to class today? Woohoo, all right, a whole one person. Okay, next question. For those of you that didn't, how many wish you would have read 6.4, 6.5 prior to coming to class today? All right. You got one more chance at it on Tuesday. We're going to do 6.6. So make sure you do that, or at least try to do that. Okay, let's go on. Let's go the other way. Sometimes we have two things that are adding together. What we want to do is we want to convert them into products instead. So this is going backwards. This is now sum two product formulas. So remember from the identities in 6.1 and 6.2, once you get down to cosine of x and cosine of y, you're done. You can't simplify that anymore. The problem is sometimes we need to simplify that some more. All right, this one is found on, let me look at it. All right, 608. So this is page 608. If you want to open it up to there. And then both sets of formulas are found 611. Because it has a review of the section, but I think for you guys, the one that you really, really want to know is all the way at the end of chapter 6. Starting on page 366, it has a review of all the formulas. So page 633. 633, probably want to look at that as far as making a 3x5 card. And 634, it has all the formulas from the chapter. Yeah.
Can you repeat that again?
Sure. On page 633 and 634, you have all the formulas we have used in chapter 6. So very, very, very important 2 pages when you're going to be building your 3x5 card. All right, cool. Almost done here. See a few people still finishing up. Cool. All right, let's go on. So we have limited time here. So using the sum and product formula, can you write cosine of 2x subtract cosine of 4x? And again, look at the formulas from the previous slide, and you're really just going to follow that formula through and through. So cosine of 2x minus cosine, and I think that's the second formula that we have there. According to the second formula, you have a -2 sine of the addition of your two angles divided by 2. So it's x plus y in the formula, so that's going to be 2x plus 4x divided by 2. Extend that line just a little bit further there. Alright, and then some multiplication of sine of the subtract the 2 formulas, divided by 2. All right, and again, negative 2. Let's see, sine, that's going to be 2x plus 30, that's 6. Divided by 2 is 3x times, and that's going to be 2 subtract 4, negative 2, have a negative x. Okay, the only little problem here is sine of negative x. We really don't want to show trig functions being a function of a negative angle. So, whole concept here, since sine is an odd function, that negative gets to be moved out. But if the negative gets to be moved out, put it out in front. Negative of a negative 2 makes a positive 2. So my final answer should be just positive 2 sine 3x times sine of x. All right, cool. Let's keep on going. All right, how about this one here? Can you give me the exact value? Or no, let's see. All right, can you simplify it as much as you possibly can? All right, let's see, sine of something plus another sine of something, that is going to be the third formula. Third formula says sine of, or 2 times the sine of the addition of the two angles divided by 2, multiplied by cosine of these, looks like the subtraction of the two angles. So 43 minus 17 divided by 2. And again, just following the formula itself. Alright, so let's see, 30, that's going to be 60. 60 divided by 2 is 30, so it's 2 sine of 60 divided by 2 is 30 degrees. 43 subtract 17. I think that's 26, and 26 divided by 2 will be at 13 degrees. All right, I don't know what cosine of 13 degrees is. That's not something I know, but I do know sine of 30 degrees. Anybody? What is sine of 30 degrees? I think I heard 1/2, is that right? It's 1/2, so sine of 30 degrees is 1/2. Cosine of 13 degrees, half of 2 is 1, so that's a lot simpler version right there here. Cosine of 13 degrees is the final answer. And it's the most simplified answer without having to punch it in the calculator here. All right, and the next one, a little bit more complicated, but I think we can still handle it here. So can you write sine of 3x subtract cosine of x? All right, and if you say, Mr. H, I'm stuck, because the sum to product formulas, it's a cosine plus cosine It's a cosine minus cosine. It's a sine plus sine. It's a sine minus. Hey, hold on. They're always adding the same trigonometric function or subtracting the same trig function off the formulas here. Let me take a look at it here, so we're all seeing the same thing here. Here's my sum. Notice the formulas are either adding cosines together, you're subtracting cosines, adding sines, or subtracting sines. There's never a time where you are sort of putting both of them together. Sine and cosine doesn't work. Okay, here's a little problem. So what we have to do is we have to change them either both into sines or both into cosines. So we choose, and it doesn't matter which way you go about doing it here. Let me just rewrite the problem here. So sine of 3x minus cosine of x. All right, you guys tell me here, what is the whole concept of the co-function identity? Remember those? What does it mean to be a co-function? Like you have tangent and you have cotangent. Secant, cosecant. I don't know. I remember covering it.
Isn't it the reciprocal?
Almost reciprocal. It's the complementary angle. Remember that? So if you say sine of 42 degrees will be the same thing as cosine of, anybody? Complementary angle to 42. Right there. Let's do this here. Sine of 10 degrees is the same thing as cosine of how many degrees? Anybody? Whatever the complement of 10 is. Remember, complementary angles are angles that add up to 90 degrees, right? So in this case, this would be cosine of 80. If you want to check it, you can check it on the calculator. Punch in sine of 10 degrees, then punch in cosine of 80 degrees, you're going to get the same exact answer. Cool. Okay, so then real quickly here, then how about this? Sine of x will give us cosine of what? If we were in angle measurements, which we're not, we would do 90 minus x. But since we are in radian measurement, because we want to be in the real part, this will be a pi over 2 minus x. We good there? Okay, so what's happening with this problem then? Let me erase all this good stuff here. So here's what we do. We say sine of 3x is the same thing as cosine of pi over 2 subtract 3x. Okay, good there. We can now substitute. So now this becomes cosine of pi over 2 minus 3x minus cosine of x. Now we got it into a form that I can now use. I have two cosines subtracting each other. That is formula number 2, or the second from the top. Okay, kind of gets weird here at first here, so let's talk about it. Formula says, again, you're following the formula. Second formula from the top. We've got -2. We've got sine of, and I think we're going to be adding the two angles together. Yep, we're adding. So this is pi over 2 subtract 3x, and we're going to be adding it with x, and then we're going to be dividing all that by 2. Whew. Again, this is our first angle right here. This is your second angle. So first angle, second angle. Okay, according to formula, we're multiplying this with sine of the subtraction of the two angles. So in case this would be pi over 2 minus 3x. Now it's minus x divided by 2. Whew, that's where all the fun begins here. So we got to simplify this little top, and if you want to do it off to the side, that's perfectly fine too. Just simplify that all together here. Maybe that's what I should have done as well here. I didn't. I just sort of simplified as I went here. So -2 sine of, first of all, this little top stuff right here, I better get a denominator of 2 for everything here. So pi over 2 stays as pi over 2, but -3x now becomes -6x over 2. And this x here plus x now becomes plus 2x over 2, all over 2. Going to the other side, sine of, again, common denominator of 2 minus 6x over 2 minus 2x over 2 all over 2. And I'm running out of space, so let me go to the next slide. Let me rewrite the bottom here so we can have continuity here. Let me just rewrite this here. That's what we had before on the previous slide. So we go -2 sine of, and let's put this together here. So pi over 2 doesn't change, it has to stay there. But -6x plus 2x makes -4x, and again, all of that is over 2. This one, common denominator of 2, so let's go with that. And -6x minus 2x makes -8x, and then all that over 2. Whew. Look at those algebra skills. Oh, wow. Okay, let's see if you guys know how to do this one here. So if you have a denominator of your top fraction, you have the numerator of your bottom fraction right here, because this is technically a fraction, it's 2 over 1. What do? We take pi, subtract 4x divided by 2. We're going to divide this by 2, or how about multiply by 1/2? Does that make sense there? So dividing by 2 over here like this, multiplying by the reciprocal of 2 over 1, which is 1 over 2, which then makes pi minus 4x over 4. Everybody good there? That's probably the more difficult algebra step right there. Cool. Sine of, again, same thing here. It's going to be pi minus 8x over 2, and then we're going to multiply by 1/2, which makes a 4 on the bottom, so pi minus 8x over 4. Okay, and one final step to do here. I think we could simplify this little 4 here, as we divide the pi by 4, and then we divide the -4x divided by 4. So final answer, let me rewrite it because I'm running out of room again. This is what I had on the previous slide. So now I'm going to go -2x, -2 sine of pi is being divided by 4. And then we have 4x divided by 4, which just leaves us just an x. Same thing here. Pi divided by 4, and -8x divided by 4. Okay, good there? One last thing we probably should try is this whole concept of identifying or verifying an identity. And so let's jump to this right here is practice problem number 5. we have to prove that the left side is the same thing as the right side. Alright, so let's go for it. Give you guys a little bit of a head start here. So can you use your sum to product rules for cosine of 5x minus cosine of x, sine x minus sine of 5x? Alright, those that are waiting for me, let's go for it here. Again, make sure you're looking at the formula, make sure you're looking at the rules here. You should have a formula next to you so you can sort of go through it. So cosine subtract cosine, that is formula number 2. So that's negative 2, sine of the addition of the angles divided by 2 times sine of the subtraction of the angles here. So that's 5x minus x divided by 2. All over. Okay, this one now, sine of x minus sine of 5. That's going to be the last formula of the 4 here, last formula here, and that is positive 2 now, sine of the difference here. So the difference between the two. So x minus 5x divided by 2 times cosine of the addition of the two, x plus 5x divided by 2. Whew. Looks hardly anything like that sign over there. Let's see if we get there. All right, and then I generally like to work with both sides of the equation. So tangent of 3x, I'm going to simplify that into, since everything is in terms of sines and cosines on the other side, I'm going to put sine of 3x divided by cosine 3x. Right, because tangent is the same thing as sine over cosine. Okay, so on back to the left side, everything is a product. That's kind of nice. The only thing I could probably get rid of right away is, how about the negative 2 and the 2? That's gone. So on top I'm left with, let's see, 5x plus x, 6x divided by 2 is 3x. 5x minus x is 4x divided by 2 is going to be 2x. With the negative in front, don't forget that guy. On the bottom, sine of, ooh, this is fun, x minus 5x is negative 4x. Negative 4x divided by 2 is a negative 2x. Notice what I do now is I put the little parenthesis in there just to make sure that it's exactly the angle that I'm talking about. And then for cosine, add it up, 6x divided by 2 is 3x. Okay, the other side, no changes here. I'm going to leave it as sine of 3x over cosine 3x. So now the question is, how could I simplify this any further? Well, again, this whole concept of, if you're having a sine of a negative angle, you can move this negative angle, you can move the negative of this angle in front, because it's an odd function. So I'm going to rewrite this, everything, and then move this little negative out in front. That's the only thing I'm going to change here. So negative sine of 3x, sine of 2x, divided by the negative of sine of 2x times cosine of 3x. Alright, on the right hand side I still have sine of 3x over cosine 3x, so that has not changed. I keep it, notice I keep the equal sign coming down. And again, I just want to make sure the left and the right equal each other completely. Alright, I ran out of room. So let me copy this down in the next slide here real quick here. That's what we had from the previous slide. And I think I got it here. The negatives cancel. And sine of 2x is actually both top and bottom. Right, see that? Sine of 2x is here. It's the same exact trig function, same exact angle. And sine of 2x is there. So now I have sine of 3x over cosine of 3x, which equals the exact same thing on the other side. Alright, again, just to torture you, I'm going to put QED. If you know what that stands for by now and you took the time like, hey, I wonder what that looks, what that is, what that means. You figured it out, and those of you that did not, then you have no clue what that means. Okay, so that is 6.4. All right, jumping to 6.5. Here's where we start finally solving trigonometric equations here. So this is the easy section. 6.6 then tends to be the more difficult section. But in this section we have to talk about what does it actually even mean to be an equation? And what does it mean to solve a trigonometric equation? And then we should sort of consider this here. Sometimes you're not given a domain, and since you're not given a domain, you have to assume that you want all the possible answers. Sometimes you're given a domain, so then you kind of think about whether that changes or not. Looks like got 8 questions to do. Let's start off a little slow and then work our way up. So there's the objectives here, but really it's solving an equation. If you can solve the equation, you got it. But you do have some ways of solving equations. So solve trigonometric equations by using the zero product property. I think you guys know something like that from algebra, the zero product property. Solve trigonometric equations that actually have multiple or various trigonometric functions in it. And eventually solve the trigonometric equation by squaring both sides. We'll see what that means. Alright, first of all, let's take a look at an example from the textbook here. So I'll just do that. Did that already here. Just for the sake of time, let's just do A and C. We'll skip B because B is very similar to A. And again, if you got this, you want to go ahead of me, go for it. If you say, Mr. H, I need some help here, let's take a look at it together. Again, I'm going to start off a little slow. I want you guys to really understand the concept of what are we doing, how are we solving it, what does it mean to solve an equation. Then once we get that down, then we'll work a little faster to get solving here. So first things first, let's look at this one here. Sine of x is equal to the square root of 2 divided by 2. How do we solve this? What does it mean to solve this? Alright, also notice there is no domain restriction here. So we want every single possible answer in the world. If there's an infinite amount of answers, we want that infinite amount of answers. So that's our problem here. Because remember, you can go around the unit circle forever, is that right? Okay, so let's go for it here. The solution. So we got one thing. We cannot think of all infinite answers right away. So we're going to have to limit our domain for now. We're going to have to limit our domain just for a little bit. So first, we find all the answers from 0 to 2 pi. Or if you think about it, we find all the answers for 1 revolution. Because you know, once you found that, you know all the other ones are going to repeat themselves. Alright, here's a little bit of work now. Now, you guys tell me here, what is the angle that if you take sine of it will give you a square root of 2 over 2? Cool, 45 degrees. The only trouble we have here is I've We already placed this guy inside radian measurement, right? So pi over 4, will that work? So we know that sine of pi over 4 makes root 2 over 2. Then we also know that sine is positive in quadrants 1 and 2. So let me make a little, maybe a diagram like this will help a little bit here. So how do we get root 2 over 2 for sine is right here, 45 degrees. Because with 45 degrees, remember you got this situation happening, right? Both x and y's are root 2 over 2. And then you have this situation happening. Because sine is positive, that means this value has to be above the x-axis. This is negative root 2 over 2 over positive root 2 over 2. But we just want this answer, right? Because that's the sine values. So first answer is pi over 4. Ooh, second answer. Anybody got this one right here?
7 pi over 4? No. 3 pi over 4.
Awesome. Yep, this one's a 3 pi over 4. All right, so here we go. In quadrants 1 and 2, here's my first angle. X is pi over 4. And the second angle gives me 3 pi over 4. Now we've got to think about it this way. Can I make multiple revolutions around the unit circle?
Yes.
Absolutely. And I could do that forever, is that right? If I start up here, this would be pi over 4. Then what I can do is I can go all the way around back to here. Now it's no longer pi over 4. It's whatever pi over 4 is plus 2 pi. So how about 9 pi over 4? Then I do that again. I have 17 pi over 4. I can do this forever. Not only I can go a positive direction, I can also go a negative direction. So I go this way. How do I solve that? I can't start writing them all of them down. So here's what we do to solve. So since sine of x has a period of 2 pi, all solutions of the equations will be given in this form here. So x is equal to pi over 4 plus 2n pi. That's the pi over 4. So notice by doing this here, 2n pi, I'm saying is I can do multiple rotations and revolutions forever. She just locked it, I think. Yeah. All right, then we got the 3 pi over 4, and we're going to do the same thing. We're going to add a 2n pi to it, and n could be whatever number I like, any integer that I like. So we have to define what n is. So you can say n is an integer, or you can say for any integer n. So here's what it means. If n is 0, then this just becomes pi over 4. If n is 1, that means we have one full revolution beyond pi over 4, which makes 2 pi. Common denominator would give you 8 pi over 4, which makes 9 pi over 4. So we simply, in a sense, we got this answer. We go this way, one full revolution, then we have 2 full revolutions. That'd be 17 pi over 4. But I got all of them. Cool. And again, that is the answer. Those two right there, pi over 4 plus 2n pi, or 3 pi over 4 plus 2n pi. I've figured a way to sort of state all the possible answers. Okay, are we good there? Yeah.
So we really don't like try to find an answer, we just find like an equation in a way?
Correct, for these, because we're just beginning it. Normally in real life, you're not going to be allowed to infinitely rotate something forever, right? There's even the whole question is, are there actual infinities? And not really in life, in real life. So normally what happens if you are rotating a airplane around a center circle or something, you may have 5 rotations and that's it. If you are looking at a lighthouse, probably the best way is a lighthouse, like a beam of a lighthouse rotating, you're going to look only 1 full revolution. So in that case, you're always going to have a domain restriction on something that's real. Does that make sense? Okay, I'm going to just check in time here and making sure I'm okay with time. Let's do, so cosine is going to work exactly the same as this one. You just have to figure out which, let's do cosine just real quickly here, just to make sure we got it. Let's go a little faster, and then tangent is going to be a little bit different. So cosine theta is equal to negative 3 pi over 2. Again, we have to limit our domain to 1 full period of cosine. And when we limit our domain, we have to say we're going to find only solutions that are in this domain from 0 to 2 pi. So in a sense, if you think about it, it's just really 1 full revolution around the unit circle. That's what I'm looking for. So now the question is, what angle gives you cosine of what angle gives you a negative root 3 over 2? Well, we've got to learn something here. When is cosine negative? Which quadrants is cosine negative? Two and 3, is that right? Bless you. Cosine is the x coordinate, so it's here somewhere. We've got to figure out that angle, and it's here somewhere. So now the question is, what is this angle here? In terms of radian measurement. Uh-huh.
Oh, 5 pi over 6.
Awesome. First angle, 5 pi over 6. Okay, then I want this bigger angle here. Boom.
7 pi over 6.
7 pi over 6. Awesome. There it is. I got it. So I got theta is equal to 5 pi over 6 plus 2n pi. And, I think so, or theta is equal to 7 pi over 6 plus 2n pi. And I got to name what n is in the world here for any integer n. Okay. Cool, done. Okay, looking at 1 full revolution, you know it's going to happen again and again. So we stick in an integer n. Okay, the only difference with tangent is that tangent does not have a revolution of 2 pi, it only has a revolution of pi. So let's see, tangent of x is equal to negative root 3. So solution for C, again, we're only looking from 0 to pi. And the reason for it is because tangent, every pi, tangent starts repeating itself. So there's no point in looking at 2 pi because you have a repeat. All right, the little trick here with tangent, I'll just sort of show you real quick here. You take this and you make it into a 1 right here. And remember, whenever you have a root 3, it's always root 3 over 2. Or whenever you have a 1, it's always 1 over 2, 1/2. So what we normally do here is we do this here. Put in a, actually, you know what I should do? One second. Let's put this little negative out in front right here, because we don't know which one's the negative, which one's the positive yet. Okay, so then I look at my unit circle. And I'm trying to find when y value is root 3 over 2 and the x value is 1/2. Except what quadrant am I in? When is tangent negative from 0 to pi? Which quadrant? It's in quadrant 2, somewhere over here. So now let's see, what are my values here? I know I have a negative x, so that means this little negative sign here actually went down here. So when, or what degree value gives me a negative 1/2 positive root 3 over 2?
2 pi over 3.
So again, looking at a chart, this is where it'd be good to have a nice, good 3x5 card that gives us these things. The angle measurement is 2 pi over 3. Perfect. And there's only once, it occurs only once. So I am done. The answer is x is equal to 2 pi over 3 plus, now careful here, it's n pi, right? Because the period for tangent is just pi. So every pi, it's going to start repeating itself. All right, let's go just a little bit more in depth on it, just to make sure we understand this here. Come on, come on, come on. So remember, for tangent is positive here, it's negative here, then becomes positive here, then becomes negative here. So whatever the answer is here for tangent, it's also going to be the same answer as it is down here for tangent. It's just the y value becomes negative, and that's okay. But we took care of it by just adding an n pi instead of 2n pi. So voila, that's kind of cool. Gives us all possible, always possible answers for that. Again, just sort of looking at time here, that's all, just to make sure we have enough. Let's go with it though. Practice problem number 1A, can you tell me that? Cool. Again, try it yourself here first. Give you guys an extra minute. Already done?
I'm not sure.
Okay. Okay, so sine of x is equal to 1. So again, we're going to look from 0 to 2 pi. And then unit circle is here. So all the way around, when does sine become 1? Sine is the y value, but the y value becomes right there, because that's the only one time it does it. Is that right? Cool, and that is pi over 2, so therefore it's pi over 2 plus 2n pi. And again, sorry, I should label this as x. X is equal to, because we found what x is. You can write it as for any integer n. You can also write it as n is any integer. It doesn't matter whichever textbook you have. The previous textbooks wrote it like that. Cool. Okay, let me skip b. We're going to skip b there because that's a cosine function. Let me jump to c. Let's skip this one. Let me jump to the tangent function. Just make sure we got it here. Go ahead, find all solutions of this equation. Express answers in terms of radian measurement. And yeah, we'll skip between radian and degree measurement quite often. Alright, trying it yourself here first, hopefully, not staring just at the screen here. I'll go this way here, probably easier. So, for tangent, again, don't forget we are just going from 0 to pi. So now the question is, when is tangent 1? Awesome by me. Yeah, I'm going over here like this. The time when tangent is actually 1 is when the cosine and the sine are exactly equal to each other. That only happens in quadrant 1 when they're both root 2 over 2. And I got a degree angle of pi over 4, and that's cool because I got x is equal to pi over 4 plus n pi only. And again, n is an integer, n is any integer for any integer n, whichever you like to say it here.
For sine equals 1, was it also plus n pi?
For the a, it was 2n pi, because sine has a period of 2 pi. All right, let's jump to the next one here. Practice problem number 2. This one has to do with finding approximate solutions. So, yep, you need your calculator if you have a calculator. All right, if you do have a calculator, let's go through it together here because there's a few little things here you got to deal with here. All right, first we need to find all the solutions for secant of x is equal to 1.5. Whoa, that's fun. Round the solutions to the nearest tenth of a degree. Now notice B. Find all the solutions of tangent of x is -2 in the interval 0 to 2 pi. Phew, great. Finally we have ourselves a domain we're working with. And that's it, just those numbers we've got to look at. Okay, also notice for A, it's also in degree measurement instead of radian measurement. So there's a few little things we're gonna do here. Okay, first of all is the whole concept of a reference angle. And so let's talk about that before we get to the problems itself. So we'll do it in terms of degrees. I'll just sort of... A reference angle always has a reference back to the x-axis. And so we'll do a few things here. I'll use x prime because that's what normally used. So if I have an angle like this in quadrant 1, notice the angle and notice it is, let's see, it's measured away from the x-axis. We good? So here's what we're going to do. We're going to say our measurement of this angle called x is the same thing as the measurement of our, I'll put this little dash mark right here. This just means prime. It just means the reference angle. So reference angle here is actually equal to the actual angle that we have here. We're good? Let me go on to the second quadrant. We'll see the difference here. I'm writing these a little bit too big, so if I'm in quadrant 2 and I figure out that my reference angle is x prime, question to you guys, how do I figure out this angle here? Okay, so think about some degree values here. Let's see, how about if, let's put in some angles in here. How about, let's say, x prime, let's say that is like 30 degrees. If x prime is 30 degrees, what would be the angle from the initial side?
30.
So boom, if this is 30 degrees, that means this angle would have to be
60.
Everybody okay with 150? Right, because it's a half a circle. So these guys are just supplementary. So let's see if this makes sense here. If I have a reference angle of x prime, the angle that I want is going to be 180 minus x. We're good there. Or let me say it this way, or probably a little better here. The angle that I want is going to be 180 minus x prime. Good there? So if my reference angle is 30 degrees, subtracted from 180 gets me 150. Okay, how about quadrant 3? How about if I have an angle here? Okay, and let's say this guy now is x prime. How do I get this full entire angle here?
270? Oh, 210.
Kind of sneaky a little bit here, but let's see. Isn't this already 180?
Yes.
And am I just really just adding x prime to that angle already? So let's see if this makes sense. The angle that I want is going to be 180, this time plus my reference angle. So let's say the reference angle is 30. That means the full entire angle is really 210. Cool. All right, and last one here as we get to this problem. What happens if we're in quadrant 4? So here's my reference angle. Let's say it's 30. How do I get that angle there?
Add it.
So the angle that I want then is going to be, let's say this is 30, right? So the angle here would be 330, right? So in this case, tell me if you guys agree here, this would be subtracting off of 360 at that point. Okay, good there? Writing that down, I think we have what we need. Again, we're going to do it by calculator here, and we have half an hour, a little over half an hour to go, so we're going to go a little bit faster here. All right, let's go for it. So first things first, when you get your calculator, secant of x, we're trying to figure out when is it 1.5. Our calculator doesn't have secant of x in there anywhere. So we have to convert it to something we know. And we're going to use the reciprocal identities. So in this case, we're going to say cosine of x is equal to the reciprocal of 1.5. All right, another little thing is, we're not going to be able actually be able to find the angle. We're going to only be able to find the reference angle. So now the next step is we're going to say we're only going to find the reference angle with the calculator. So cosine of x prime equals 1 over all right, with that said, then we're going to list here. Again, one more little step, just some algebra here. Here's what we're going to use. We're going to use this right here. So if cosine is in the other, the only way we can cancel cosine is if we take cosine inverse of both angles. That's kind of what's done here. So cosine on one angle cancels this off by cosine inverse to the other angle. Okay. All right, so now let's go for it here. So first of all, when you get your calculator, we've got to do a few checks here just real quickly. If you guys go to your mode on your calculator, you have a choice right over here. You got a choice of being in either radian mode or degree mode. Since the problem says degree mode, we've got to change it to degree mode. You can do one of two ways. You can either punch in this cosine inverse of 1 over 1.5, enter, and that's going to be in radian mode. Then you're going to take that answer and multiply by 180 divided by pi, which will give you the, probably don't do it this way, probably do it this way. Let's just change this guy into degree mode. So go to the mode function in your calculator. It's towards the top row there. I think it's the second or third button there. Scroll down and you're going to have a little flashing cursor. Go over to degree and click enter. So that means the degree will be flashing and the radian is not highlighted anymore. Then click quit, so second. I think it's second mode. And now let's enter. Let's enter this right here. We're going to enter cosine inverse. And as soon as you enter that, you're going to have a parenthesis open up. You're going to put 1 divided by 1.5, close off that parenthesis, click enter. You got yourself a 48.2, I guess. So now, the question is, which quadrant are we in? And it goes back to doing this thing right here. Let me just do this real quickly here. In quadrant 1, all functions are positive in quadrant 1 because positive x, positive y. In quadrant 2, only functions that are positive is sine of x and cosecant of x. Quadrant 3 is tangent and cotangent, and quadrant 4 is cosine of x and secant of x. Those, again, I'm giving you which ones are positive here. For cosine inverse, we only need to figure out 2 quadrants where cosine is positive and cosine is negative. That's how it works. So for cosine works right here. Cosine works positive here and negative in quadrant 2. So we just need a negative and a positive quadrant here. Notice 1 over 1.5, that's a positive answer. So we know that we are in quadrant 1, so we can just say Q1. If it was a negative, if we're trying to figure out secant x equal to negative 1.5, that means we would be in quadrant 2. Then we'll have to use the reference angle. So since we're in quadrant 1, our reference angle is actually, let me go back like this. Our reference angle of 48.2 is actually the angle itself, right? Since we're in quadrant 1, the reference angle is actually the angle. All right. The only thing is it says find all solutions. We've got to find all of them. And so if we have to do that, then we're going to put 360 degrees times n, just like we did 2n pi. Since we're in degree mode, we just put 360 n. Okay, but cosine is also positive in quadrant 2, is that right? No, cosine is negative in quadrant 2. So we're going to have to deal with looking at quadrant 4 as well, right? Because cosine is going to be positive here and here, and I got to find all the solutions. So now we're in quadrant 4. So my reference angle I know to be 48.2. So my question is, what's going to be my real angle? Anybody give me that? Let's see, quadrant 4, isn't it 360 subtract what we want out of it? Why do I have a 4.8? It should be 48 here, so 48.2. All right, so the real angle would be 360 subtract 48.2. Anybody got that? Nobody's talking to me. 311 degrees or 0.8 degrees. Now that's just once, right? Finding all those solutions, we're going to add 360n. And now we have to specify what n is. And we say n is an integer, or for any integer n. I should do it here, though, as well. For any integer n. Sorry for the chicken scratch there a little bit. Okay, we're getting somewhere. We're gonna go really, really quick through the rest of these here. Okay, part B. Let me go back to what it says to do first of all. It says find all solutions of tangent of x is equal to -2 in the interval 0 to 2 pi. So we're gonna go one full revolution. I gotta figure out where those are. Round to 4 decimal places. So let's jump to it here. First things first, tangent of x equal to -2. And we're going to go only from 0 to 2 pi. We are in radian mode, so we'll get there when we get there on the calculator here. But first of all, we should notice this right here. We're going to really figure this out. When is tangent inverse? What is tangent inverse of -2? Well, we got a small little problem. When you're going to do tangent inverse of -2 in your calculator, it's going to give you some bizarre answers. Okay, so what we do, kind of pay attention here because this will help you out here. What we do is we forget about the whole concept of it being a negative number, and we only want to find the reference angle. And the reference angle, we always make the value positive. We're just trying to figure out what it is in quadrant 1. We're just trying to figure out the reference angle. So reference angle, tangent of 2. Now don't forget, we are in radian measurement, right? So we got to go back. Now go back to your mode on your calculator, and you're going to click radian measurement. Make sure it's highlighted. Okay, and then find for me what's tangent inverse of 2.
1.1.
Awesome. Okay, 1.107 or something like that.
Yeah.
4 decimal places. This is what we found. We found in quadrant 1, we found tangent to b is 1.107. 1. Got a little problem because that's not our angle answer, right? That is just the reference angle. So now we go back to our problem here. 2, 3. Our original one was negative, is that right? So you guys tell me here, which quadrants is tangent negative? Three, that's when the tangent's positive, because you got a negative over a negative.
2.
2, yep, you got it. So let's go for it here. Let's look at quadrant 2. It's here. And then also quadrant 4. So those two quadrants. So real quick here, if my reference angle is 1.10715, what's my angle? Carefully, you're not in degree mode. You are in radian mode, so we've got to develop some other tricks here. So remember, in quadrant 2, we would subtract, right? In this case, what we're going to do to get this angle here, we're going to have to get, let's see, pi subtract this guy. So what is pi subtract 1.10715? Probably do it on a calculator. I'll go with the answer 2.0344 if we did it correctly. Is that right?
Yeah.
So that's pi subtract that. Now we're in quadrant 4, so we want this angle now. Boom. So remember with degrees it's 360, subtract that angle. Now it's going to be 2 pi subtract that angle, and x is equal to?
We use 2.0?
No, we use this angle still, because that's our reference angle. Awesome. 5.176 and 0, because we have to go out 4 decimal places. Okay, got 20 minutes here. I'm kind of just looking at I think we can do the rest here pretty quickly here. Let me skip practice problem number 3 just for a little bit here. Let's jump to practice problem number 4. We'll skip 4 because that's just a word problem here. Let's go to 5. We'll go 5, 6, 7, 8, and then come back if we have time. We'll come back to that one here. So let me just check here. Practice problem number 5. Alright, so let's go for it here. So this is what normally how we see it here. So find all solutions of the equation, and there's some equation there, and then you're always given an interval. And that interval not only restricts your domain, but it tells you what the answer would look like. Is it degrees or radians? So if you see 0 degrees to 360 degrees, you know you're in degrees. So let's go for it here. So notice this is called the zero product property. Remember, this one is when you used to factor, and you factor something into like x plus 2, x plus 3, or x plus 2 times x plus 3 equals 0. You can split them off into 2 different pieces. It's exactly what we do here. The zero product property says if I have 2 things multiplying each other, they give you 0. What I can do is I can split it off into sine of x minus 1 equals 0, or square root of 3 tangent of x plus 1 equals 0. And what we do is we solve each of those. So I'm going to go just a little bit faster here because of time constraints here. So keeping up if you can. If I'm really going too fast, tell me. I'll slow down a little bit here. Don't want to get you guys lost either though. Alright, add 1 to both sides. We're looking at sine of x equal to 1. So thinking about that here, let's see, when is sine 1? I think it's at 90 degrees, but I can't say degrees. I have to say radian measurements, so pi over 2. And I'm looking for 1 full revolution. So I'm looking all the way around 1 full revolution. When does sine equal 1? There's only once when it happens. That's pi over 2. Then I start solving the other one. Oops. I don't know why, but it's there. Okay, let's see, subtracting 1 from both sides, dividing by root 3 gives me a negative 1 over root 3. And the trick is, with tangent especially, because you're forgetting that little 2 there, you make each of these into fractions here. The negative 1/2 over 3 over 2, or it could be that the negative was actually down there. Good? You got 2 choices. You don't know where the negative is. So now let's take a look at it here. Let's see, when would you have a negative there? So let's look at quadrant 2, because I know tangent is positive in quadrants 1 and 3. So I'm going to look in quadrant 2. And in quadrant 2 I got my negative root 3 over 2 and a positive 1/2. But what's my angle that makes that true? Think I heard it, 5 pi over 6? I go with that. Alright, then I know tangent is also negative in quadrant 4. So let's set up 4 over here. And that one's going to be, let's see, positive root 3 over 2. The x value is positive, the y value is negative. And then can you give me that angle? I go with 11 pi over 6 is perfect. Boom, 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 boom. Cool, there it is. I got 3 answers here. That's when this happens. Okay, going a little faster here. This is called the zero product property because you have 2 things multiplying each other give you 0. Sometimes we do have to factor. So here's some algebra and trigonometry together at once here. Can we find all the solutions of 2 cosine squared of theta minus cosine theta minus 1 equals 0? Oof. Got some factoring on my hands here. Alright, what you should think about is something like this. Oh, sorry, I'll let you guys write down the problem first though. This kind of gets a little strange here, but how would you solve something looks like this? You just factor it down, is that right? Factor down into, let me guess here, 2x times x here. How about a minus 1 here and a plus 1 there? Would that do it? Is that the factored form? Well, in a sense, our x is that cosine theta. That's sort of our x value here. So if you want to see sort of, that's the algebra example, but let's do the trigonometric example, okay? So let's jump to this one right here. We've got to solve this. We're going to set up just like we factor down anything else. Only way I can get a 2 cosine squared theta, 2 cosine squared theta, the only way I can do that is 2 times cosine theta in one parenthesis and cosine theta in the other parenthesis. Breaking down negative 1 so that in the middle I can get a negative cosine. So that negative 1 breaks down into a minus 1 here, plus 1 there, and I just check the middles. Do I get a negative cosine theta in the middle? Oh, hey, this looks like the previous problem, isn't it? You got 2 things multiplying each other? But let's just check. Make sure we get the middle here. Make sure we get a negative cosine in the middle. So 2 cosine theta times negative 1 makes negative 2 cosine theta. Cosine. And the bottom value, 1 times cosine theta is cosine theta. And the question is, do those add up to give you a negative cosine theta? I think so, right? So that one adds up to the middle. Okay, cool. So let's split them off then. This guy's equal to 0, or this second parentheses equal to 0, and can you solve each of those?
Yes.
Okay, due to time constraints, I'm going to do it with you. So subtract 1 divided by 2 gives you cosine theta of -1/2. This one we're going to add 1, so we got cosine theta of 1. So can you tell me when along the unit circle do you have a cosine value of -1/2?
2 pi over 3.
It's negative, so you know you're going to be in quadrants 2 and 3, right? And so you're looking for something looks like this, and you're looking for something looks like this. So 2 pi over 3
Yes, and 4 pi over 3.
and 4 pi over 3. Okay, now remember how it says find all the possible answers, right? So for each one of these answers we're going to put in theta is 2 pi over 3 plus 2 pi n, and then for that other angle there you're going to put 4 pi over 3 plus 2 pi n. Okay, when is cosine equal to 1?
2 pi.
You can say 2 pi, you could also say 0, right? Right at 0, because you don't move anything off of the unit circle. So it should be 0, so theta then is just 0 plus 2 pi n, or just 2 pi n? Whoa, now how many wish they would have read ahead? Mr. H, I wish I would have read ahead. Okay, let's jump to practice problem number 8. And that's the more difficult one, and then we'll look at one little weird thing that sometimes happens here. So let's jump. Whoa, sorry. Let me get rid of this here so it doesn't bother us later on. Okay, so here's what we got. We got to find all the solutions of the equation. Square root of 3 cotangent theta plus 1 equal to square root of 3 cosecant theta. We're constrained by our domain. That's kind of nice, 0 to 2 pi, so we're good there. Okay, here's our little problem. Notice you have a cosecant and then you have a cotangent. I got two different trig functions on my hands. I can't deal with that. I have to have one single trig function if I'm going to solve this. So I have to somehow think about how am I going to change all of this into the same trig function. And there's a little bit of a clue here. It says solving the trig equation by squaring, and that's exactly what we're going to do. And the reason why I know to do this is because I have a little rule that look at your trig identities and see if you can find any matchup between cotangent and cosecant. Is there any kind of rule that sort of establishes one with the other? No, not that, but anything that connects them. Anything, like reciprocal identity, are they reciprocals of each other? Are they Pythagorean theorem triplets? Or something looks like this. It's one of the Pythagorean theorem identities. 1 plus cotangent squared x is equal to cosecant squared x. Again, this is going to be a long one here, so let's go with the writing process here. So here's what we're going to do. There's no way I can get rid of a cosecant or cotangent if they're in their linear form. I got to get them into their square form. So here's what I'm going to do. I'm going to take the right hand side, I'm going to square that side of the equation. I'm going to take the left hand side, square that side of the equation. Okay, good there. And again, let's go with it here. Lots of writing to do here. So this is a binomial, right? There's something here plus another something. So off to the side somewhere, you got to do this here. So root 3 cotangent theta plus 1, another root 3 cotangent theta plus 1, and start foiling things out. Root 3 times root 3 is a 3. Cotangent times cotangent is cotangent squared theta. Doing the outside term, root 3 cotangent theta times 1 is just going to give me root 3 cotangent theta. The inside term, 1 times root 3 cotangent theta will give me another root 3 cotangent theta. And at the end, 1 times 1 is 1. So that's the whole entire left-hand side there. Whew, man, got factoring, got a whole bunch of weird stuff here. Okay, I'm going to move just a little faster here so you can keep up. So the only thing I can condense is this little middle section, right? You got root 3 cotangent theta, another root 3 cotangent theta, so I got 2 of these guys. So how about, oh, on the other side, sorry, I'll show you the other side. We squared this side too here, so root 3 squared gives you a 3. Cosecant squared gives you cosecant squared theta. Okay, simplifying this side here, I got 3 cotangent squared theta plus 2 of these guys, so 2 root 3 cotangent theta plus 1 on the left, and this does not change on the right. Okay, but now finally, so notice which way do I want to go? Do I want to change cotangents into secants, or do I want to cosecants or cosecants into cotangents? So do I want to change this guy into cosecant? I don't, because notice real quick here, I have a linear form of cotangent here. So then what I want to do is I want to change everything into cotangents. So this guy now, notice cosecant squared is actually 1 plus cotangent squared. So that's exactly what I'm going to do. I'm going to change this guy into 1 plus cotangent squared. So everything else remains the same. 3 times 1 plus cotangent squared theta. Oh, sorry. Cool. Okay, we got that. Finally, we got everything in just terms of cotangents. So I finally got it back to just a single trig function. And yes, 6.6 is even more difficult. So you got to master the 6.5, because then we start throwing in the half identities, sum to product identities into these equations here. Okay, so you should know, you should be able to, distribute the 3 at this point, right? 3 times 1, 3 times cotangent squared theta. Let's see what I got here. Yep, so distributing the 3 gets you that. Okay, I think we'll might stop with this one here today. Okay, now what do we got to do? We have to, I see cotangent squared, so I'm going to move everything over set equal to 0, right? Just like we do with x squared. So let's move everything over. Subtract 3 cotangent squared theta over here, and something very nice happens. All my cotangent squares have disappeared. I love it. They canceled off. So 2 root 3 cotangent theta minus 2 equals 0. Cool. Like that. Okay, one of them to solve. That's it. Okay, so let's see. That means I'm going to solve for a cotangent at this point then. Since I don't need to factor anything, so I'm going to add 2 to both sides. Divide by 2 on both sides. Or divide by 2 root 3. The 2's cancel, leaving me with 1 over root 3. Okay, so notice first of all, it is positive. So with cotangent, I know I'm in quadrants 1 and 3. But just like tangent, 1 over root 3 doesn't tell me what the unit circle quadrant is. So we're going to make that 1 into a half, root 3 into root 3 over 2. So remember, either both are positive, or it could be that both are negative, because that will give me a positive 1 over root 3. Alright, so let's look at quadrant 1 first. Quadrant 1 looks like this. My coordinate is x is a positive 1/2, y is a root 3 over 2. And you guys tell me, what angle is that?
5/3.
I go with 5/3, okay. Then how about if we get a negative 1/2 and a negative root 3 over 2? What angle is that? There's my pi over 3.
4/3.
4 pi over 3. Perfect, okay. We've got one little small problem. Whenever, and this is from algebra, this is whenever we started solving, remember radical equations? Remember the ones that had square roots in them? From algebra, remember whenever you squared both sides of an equation, you might have got extra answers that are not there. Remember we called them extraneous roots? Hopefully we called them extraneous roots. So whenever you square both sides of an equation, there's a possibility that you have an answer that's really not an answer. So we have to check. So we got to plug it, and again, don't want you guys to do this here because we have lack of time here. But you'll have to test pi over 3. And you have to put in pi over 3 back into your original equation. And you got to see whether they are going to match up or not. So pi over 3 is here. Start simplifying stuff out. You find out with, whoa, that's kind of cool. It does work. So pi over 3 works. Then you got to test the other one. Again, don't want you to test it, lack of time here. So let's test 4 pi over 3. Back into the original equation. Testing 4 pi over 3 into cotangent of 4 pi over 3 plus 1 is the square root of 3 times cosecant of 4 pi over 3 is in quadrant 4. Again, these are the x and y coordinates. So cotangent turns out to be a positive 1 over root 3. Hey, we had that before, huh? Plus 1. And root 3 cosecant of 4 pi over 3 turns out to be a negative 2 over root 3. Is that right? It's the reciprocal of the y coordinate. Cool. All right, simplifying the root 3's go away. I love that. So 1 plus 1. You got the root 3's cancel off here. You got a minus 2, but then here's my little problem. Hey, 2 does not equal negative 2. Alright, in this case, 4 pi over 3 does not work. It's called an extraneous root. It only appeared because we squared both sides of an equation. The only answer here is pi over 3 is our final answer.